Good evening. Thank you. We're ready to start our meeting. This is our January meeting, and we're glad that we have so many folks here, and I think we've got about 35 or so on the Zoom meeting. So a full house, even if it doesn't look like it's a full house. Come on now, behave. The general business that we'll be doing tonight, we have member presentations from Wayne Thomas. We also have one from David Douglas that we didn't list there. And our speaker is Dr. James Jackman from ASU. Do we have any visitors tonight? Okay, we have a plethora of visitors. Let's start at the beginning. If you guys could tell us, stand up, tell us who you are, where you're from, your favorite superpower, or whatever you would like to share with us. Okay, Mark Hunt, thank you. And yes, sir. Tony Johnson is the BFF or the second or whatever. Okay, next up. Yes, sir.
Back in the early 90s, I've been wanting to become a member for a long, long time. I actually also thank you. So glad to be here, and I'll be signing up next week.
Cool. Dan Beck, thank you. Also, next.
My name's Aaron. I'm here with my uncle Dean, who is a member.
Okay, Darren, thank you. Anybody else that we didn't get to? Oh.
Brandon.
Okay, Brandon, thank you. And next, yes, sir. Okay, Rick is in James' class, and we are envious that he lives in a dark sky neighborhood. So good thing. Thank you. We are glad that you are here. We really do appreciate visitors. We can't really deal with visitors on the Zoom, but I'm sure we may have also had a few new folks, since I saw a good number of emails of people requesting information about the meeting. So thank you. We're all glad that you're here tonight. Just introduction of officers and boards for 2023. I'm Claude Haynes, the president. Woody Sims is the vice president over on that side. James Yoder, everybody's gathering in the front. Brooks Gofield is gathering the back. He's the treasurer. And then our board members, Don Wrigley is covering the observatory tonight. Tom Mosden is also up front. Steve Bradshaw was here earlier, but he's had to leave. Alex Beck, there we are. Alex is over there, and Dave Kosho down front, Dave Kosho. So if you have any questions of things, you're welcome to go and attack any of us. We would be glad to help you and answer any questions and point you in the right direction for whatever. James Yoder is also our property director, and Marty Pazanka is the webmaster and newsletter editor. I think we conned Brandon and Marty into working tonight because they're working on doing some updates on the website, and it'll make it easier for them to get together. So tonight, we want to do just a little kind of housekeeping to begin with. We want to keep in touch with you, and the best way for us to do that is if you are members of the of our mailing list. So on our website at EVAC Online, back to where you were supposed to be. I'm going to try this again and see if it now will do what we want to do there. So on the home page, there are all sorts of fun things that are useful, and we're going to be talking about them in a couple of sessions. My talking about events and Wayne talking about our observing program. But if you need to know about the monthly meetings, you can click here, and that will also take you to the pre-recorded Zoom meeting. So if you've missed something, there's a list of all of that information as well. Stop doing that. Observing programs, we'll talk a bit, but Virtual Beginners Lab is also a great Q&A resource. Here is a link to the website for the observatory itself. It's a separate website. Just click more info. We'll talk about that when we do events. And then down here, it is subscribe. So if you just click sign up, this will take you out to free lists, which is the group that we use for our email. I apologize, it's a site owned by another company, not controlled by us, so you will find lots of weird ads. But if you simply enter your email and now you click subscribe or unsubscribe, if you want to drop off the mailing list, if you move and whatever, you can unsubscribe. There are also options for digest, so if you want to put any, if we sent multiple things, you would get them put into one, or you can go to vacation. But basically, this is a way that you would subscribe to the EVAC announce. We'll talk about another website, another list in a little bit. But Tom has worked hard to clean up our mailing list. We had, how many? 500, there were tons. How many? It was almost 800. We're down to like less than 400 now. So we have cleaned out and tried to maintain the list. But if you want information, all we do is really do an announcement for the meetings or any large events or things that we think membership should know about. If you reply to that message, it now goes to the person who wrote the message. It's kind of a one-way street, so you are not able to yourself to create announcements on EVAC Announce. But if you do have a question, you can click reply and it will go to whoever generated that message, either myself or Woody as vice president or Tom, the people who would be sending out those pieces of information to you. Also at the bottom of this page, if I can go back to there, further down, you'll find some wonderful pictures that have been added in, and then a contact us, which shows the location of the observatory and the library here at Greenfield and Guadalupe, and quick links so that you are able to contact me as president or to our webmaster or any of the other officers that you should be able to or might need to interface with. So that, I hope, gives you some good ideas about contacting us and participating in the programs of the club, and also will give you a way if you sign up so that we can be in touch with you. Because we do have some folks who had been previously on some separate lists, trying to consolidate those and just make it easier for us to manage. It's very helpful for us to do that. So thank you. And I would like to mention Bill Peters and John Gerger. We have a card in the back to sign if you want to for Bill Peters' family, and I hope you've written or signed some information or signed your name to do that. Bill passed away in December while he was observing by himself. His memorial service was early in January. Unfortunately, John passed away in November. Joy Baker, who's not here, but just called him up at random to say hi and wish him a happy new year. And we discovered that his phone had been disconnected. We don't have a card for John because we have not been in contact with any of his relatives. So it just happened. It would be useful if we would just take just a moment of silence to kind of think happy thoughts. And if you remember John or you remember Bill, they were both long-term members of the club. John was an assistant manager at the observatory, and they worked very hard, and we are going to miss them. We are all star stuff. So tonight, our treasurer's report from Brooks, the bean counter. Are you from Boston? What's it with the beans?
Yeah, for those of you who are new, I'm Brooks Schofield, EVAC Treasurer, newly elected. For those of you that have been here a long time, I'm Brooks Schofield, EVAC Treasurer again. So, oop, wrong way. There we go. 2022 is a really a great year for us. It was kind of a good news, bad news thing. COVID had people cooped up for quite a while. They came out, they had money to spend. They wanted to see things. They wanted to do things. It was really a nice year. So at the top line there, the number on the EVAC side represents a lot of money from the observatory visitors things that Claude has been running. And we had a tremendous auction too. We had accumulated quite a bit of equipment and we auctioned that off. We did very, very well. As you can see, expenses are kind of about like we thought they would be. We netted about $12,000 on the year. So that was just absolutely outstanding. Looking forward to 2023, 2022 was a different year, just like I said. People wanted to get out. We had a large equipment collection from years and years that we auctioned off. And the membership receipt was stable. I was a little afraid when we got into this, especially going on with the web, that we would see a membership drop off because people would start, watching from home and forgetting to actually join. And that's kind of why 2023 looks a little less robust. The economy is not looking quite as good. Fixed costs are up. We're heavily invested in Zoom now. Web costs are up. In fact, I made this slide up about a week ago, and today I got a message from our webmaster saying we're having to change away from one vendor to another vendor, and it ain't getting cheaper by a bunch. Also, and more people are Zooming our meetings. We've got a lot wider footprint now with people, but it's expensive and everything is going up like printing. I went over to the printers because sometimes I would send in something. I don't have a printer. I would send something over to the UPS office near me. It used to be 10 cents. I sent one in about a week or so ago, and I went over and they told me it was 25 cents and a $2 charge for sending it in. So I've gone to another printer, but it's just more expensive. Paid membership is critical. I'm really happy to see a lot of people here this evening. The forms are available at every meeting and online. We take PayPal, we take checks, we take cash. We do not do credit cards or Zelle or anything else that would indicate we are a business, because there are a number of flaming hoops to jump through and it's expensive and we don't net anything. In fact, PayPal even went from 3% to 5%. So nothing is cheaper. The last thing is I have a list of badges awaiting new owner. It's not quite that bad, but we were working on it. There's 49 of them. Claude said he would publish a list. We will get a listing up of last names that I have back there so that people that have ordered a badge and forgotten them, who are old like me and have senior moments, can come and pick them up. Otherwise, I will make the same offer that I made a couple of years ago. If you're thinking about going into witness protection, we can really do some deals on a new identity back there for you. Any questions? Thank you.
Thank you, Brooks. We do appreciate that. And I would say if you just wanted to pick up a random badge and assume a name, that seems to be what people do nowadays. So we have them available. You can be who you wish to be. Shirts. Let's talk about clothing. We have some shirts left in the over on the table, shirts and hats. There's a sign-up sheet in the back for these type of shirts. The what are these called? Polo. Polo. All right, as opposed. And then we also have a sign up for hoodies. The issue is we need to get a certain volume to get a discount for those prices to apply, but we're trying to see if we can do those. I would also like to see, and maybe you can also poll this with Tom if you have a preference on Zoom, how many of you would prefer just a regular t-shirt with the EVAC logo? Hand up, 6, Dave. You don't want a t-shirt. Okay, never mind. All right, we got about 8 there. We may next time be able to take some orders for t-shirts as well. The issue for this is we are not a clothing boutique. And so we will see what we can do with all of those. I know unisex shirts don't fit well for ladies. So we will see if we can see how many requests that we have, but that helps to see that we might be able to get maybe an order of t-shirts for next time out. So thank you. So if you haven't on the way out, sign up. If you would like one of those shirts, we will order extra. So if you can't make a decision tonight, that's fine. I don't know how we deliver via Zoom. Maybe it's we'll fax you one. So tonight, I would like to talk about our outreach programs. We all know that astronomy is the gateway drug to science. We got hooked on that drug long time ago. Now, I'm sure people could argue that dinosaurs are the gateway drug to geology or trains are the gateway drug to mechanical engineering. But for us, it really is a gateway drug to the fields of science. Now, we do a lot of outreach. The first outreach we would have would be with the observatory, and we have a good, loyal staff, but we've also lost a few members to retirement, or John in the case of permanent retirement. And if you are interested in volunteering at the observatory, let me give you a few guidelines. You will know lots more than anybody who comes to visit the observatory, except for young Sheldon, who's majoring in quantum physics at 11 years of age. Otherwise, what we have is someone inside the observatory who is showing people the object. There will be people who will move the telescope and go from one place to another. But we need people at the door to simply answer questions and to shuttle people in and out. We need people who will work the line, especially when it's really, really busy, to simply say, is it your first time here? And then to go through the spiel, oh, you need to come back. We're open every Friday and Saturday, sunset till 9:30, weather permitting. You can see it flows off the tongue because I've done it so many times. So it isn't that hard. I don't want people to think, oh, I have to be a super expert observer. If you would just like to be able to participate and to have some fun and to really make a difference in the lives of young people, I would recommend volunteering at the observatory, or to join us as Wayne and Steve and Brooks and I did last night at Skyline Gila School. It was a really neat school. This is one, talking with the teacher, the school, some of you may have years ago been down to the Gila Reservation, Bop Shul. This is a school that was at Bop Shul and has now moved to Riggs Road. So it's in Chandler Unified as a school, but most of the kids were Native American. They were really polite. It was a wonderful, fun evening. We had a great time. And again, if you have a telescope and you want to share it, you do not need to be a super observer. You will park on one bright object. I spent a good bit of the time last night on Venus, and then I switched over to Sirius. I was working on bright objects. The great news of Sirius is you have a fun catch line. If you're making a wish on the first planet, you see it, first star you see at night, it's often a planet. And that's a way to make an impact with kids. The second one is for Sirius. The light from that star is about 8.5 light years away. So that light traveled 8.5 years to reach your eye. How old are you? I'm 7. So that light was a twinkle. That twinkle was left before you became a twinkle. So there are wonderful things that you can tell to kids to get them involved in astronomy, and you do not have to be a super expert. And so if you have a telescope and you want to share it, The best thing is to see the faces of kids or their parents or grandparents who also come with them to those parties, and they may never have looked through a telescope before. And now this is just something that's fascinating to them. So we really encourage you to join us in our outreach programs, not to be intimidated by that. We have a good number coming up. We had the science night last night at Skyline Gila. We have a senior living facility. This is one of the first ones we've done of those. I think we've got a couple folks for that to cover, but we have a STEAM night at Bologna Elementary School. I don't know if it's Bologna or Bologna. I can't tell. But we do need some help on that on Friday night. Wayne is hosting and helping the library with some telescopes that they have acquired. So he's working on Florence. I think we've got enough folks for you, but maybe one other person could join. Redbird Elementary, a science night at Santan Elementary. Mountain Bridge Community Association. This is a homeowners association that called us with a night for their residents. And so we'll give it a try. We haven't done these before. And then if you know Henry at Chandler Community, Gilbert Community College on the 23rd, we'll be doing an event there as well. And that's always been a very, very popular and busy night. You can email me, which now, because we need an events coordinator, and this is another reason why I'm making the speech, because it would be helpful if somebody would like to volunteer to be events coordinator. You can mail to volunteer, but here also is the best way. If we go back out to what I can go to here, go to free lists. If you do find and join, and you can close your stupid ad, sorry. But if you do a search here for EVAC, you'll find the EVAC announce, you'll find an EVAC board, which is just for the board members so we can communicate board meetings and information. But if you go and click on EVAC outreach, it works exactly the same way. Just put in your email and subscribe. Now you may get, if I can't recognize your name, because sometimes names, email addresses do not include your name. They are just a pseudonym. But I will then send you an email to say, hey, who are you? Just to let us know, and I can put your name in on the list. But to make sure you didn't accidentally also sign up and thinking you were going to announce, because we've had that happen before. Because if people search for EVAC, then they'll find these and they try to join all three. But this email address is a list group that's just for the people who are going to be volunteering for our EVAC outreach. That way we don't have to send an announcement out to hundreds of people. We can now just communicate among ourselves. This is how you get into the parking lot. Sunset is, the event starts at 5:30, but sunset is at 6:15. So just arrive before 6:15. Here's how you get in. Or it's rainy and cloudy, the event is canceled. And so this way we are able to have a limited group of the people who are actively involved. And we want you to sign up for that to help us. Does that all make sense? Any questions on the outreach things? One of the things that really distinguishes the club has been our outreach programs. It's one of the reasons I think that we have grown as a club, because we have made contact with all sorts of people. I had somebody last night who said, oh, I have a telescope. This would be a lot of fun. Yes, it is. And so we may have a potential person who will join the club, but also help us with outreach. And we hope that you will find this to be something that's meaningful and useful to you. Some of us are getting a little older, but if you remember back years ago with Randy Peterson or to Lynn Young, we had a very active group before the pandemonium. And for those of you who remember, we're doing a star party, and the contact person is Randy Peterson's daughter-in-law. And we're doing another star party that I talked to him this week, Howard Israel's grandson. So if you remember back 10 years ago or so, Howard was a really active member. If you're curious, yes, Maddie is still alive and living in the same house that she and Howard shared. Good for her. So it is a small world, but we want you to help us with outreach. And if you do have any questions, just give me a message, either through president or events or whatever. But we do hope that you'll join us, and we do hope that you'll be able to keep this going for a long, long time. Yes.
Do you want to mention the Friday night, second Friday?
Yes, one of the things is that we do second Friday, and I didn't mention, I'm going to go backwards. Thank you, sir. That was helpful. If I go back a slide and I click to here, if I'll go back to any one of these and I click events and meetings, this is also something that's handy, and this will come up in just a second because Google's a little slow. But there's a calendar that shows up on the events page, and this lists all of the events. So if you click here, this is the second Friday Star Party that is at the observatory. We use extra telescopes in the lawn nearby. We have a lecture at 7:30 for kind of a general purpose lecture, a little less technical than I'm assuming we would have tonight. Don't know. But that is our second Friday Star Party. Here we would see, this would be just a typical announcement. And here we would know the number of attendees. You could click this, you can add it to your calendar. Sorry, Google Calendars. But this is how we would also give you some information. So if you click on this, that's the Mountain Bridge Community Association. So this is how you would also find out what's going on. We list the meetings, we list the second Friday, but we also list any of our events. And so, great, good point. Yes?
We're not using the sidewalk anymore.
We're testing because we had some issues with the traffic and the darkened parking lot, that we think that we can just roll things into the grass area by the observatory. That gives us more room, and that is simpler. They will not allow for vehicles. So then that may not be one that you would want to volunteer at. But if you have a lighter scope or you have a cart, it's not too hard to get in. We had 3 folks last time and we just schlepped things in and out. But it's a good point. Okay. All right. That was good. Thank you, Dave, for reminding me of that. Talking about our observing program is Wayne Thomas.
Good evening. I'm Wayne Thomas, the person in charge of giving you awards for the observing program. My first slide was, why do we have observing programs? My pitch is really to those of you who are newer to astronomy and haven't really developed your way of doing things. So one problem that sometimes occurs for those of us that might be new is, well, let's see, what am I going to look at tonight? Well, there's the Orion Nebula, there's Jupiter, there's Saturn, and then what am I going to do? The observing lists give you a canned way to approach how you're going to observe. So we have observing lists that are easy. We have observing lists that are hard. And if you start with an easy one, such as planetary nebula, I think there's maybe 50 planetary nebula, or maybe only 30, or globular clusters. I think there's 50 on that list. These are relatively easy things to do. Or if you want to tackle the Messier list, there's 110 objects in that, and they're not terribly difficult. So what I wanted to do was share with you some of the navigation on our website. So let's see how this works. Some of these are quite challenging too. If you're an experienced observer and you want to really get a challenge, you can try the second Herschel 400 or the Hickson 100. Some of the Hickson objects are as faint as magnitude 15.5, or the globular clusters in the Andromeda galaxy. you know about globular clusters, try finding the ones in the Andromeda galaxy, or ARP galaxies, which are pretty faint, or able clusters of galaxies. So if you're going to select an observing list, I have a few recommendations. First, what are your resources? Do you have a large or a small telescope? Can you get down to 12th magnitude? Maybe, maybe not. Are you willing to observe for several months or a year or 2 years in order to complete a list? Even if you're not, you know, pick a list, get started. What have you got to lose? And then the advantage of trying one of these lists is that you rub elbows with other astronomers and you can talk about it. Where are you? What do you still have to do? What's holding you up? It becomes a way to share what you're doing. Now let's take a look at the observing list programs. So let's see.
Move the mouse to that screen so you can scroll down. Is it letting it? Let me try one second.
I'm seeing somebody else's.
Here it is.
I'm seeing somebody else's.
There, you should be able to.
Okay.
God knows. Okay.
So here are some of the easier programs for starters. The Messier program, the globular cluster program. Maybe not the EVAC 200 for starters. Planetary nebula are good. I think I started with the globular cluster program, and I had trouble with that until I got a really good alignment at the Riverside Star Party. And with a high altitude and clear skies, I was able to check off, I think, at least 10 globular clusters in one night. Planetary nebula are good, but I would recommend that you have either an oxygen 3 filter or an ultra high contrast filter so that you can blink what you're seeing. If you look without a filter, you see a star field and you're not sure which might be the planetary nebula. But if you use one of those filters and kind of pop it in and out, then the planetary nebula comes through bright and all the stars fade when you put the filter in the line. I've not done the binocular Messier. I think I'm stuck on the open cluster star program. I think I have 2 or 3 clusters left to do. They're in the south and they're only at a certain time of year, and I still have to get out there at the right time to do that. The galaxies program is good, but some of those galaxies are pretty faint. I've looked at the Palomar globular cluster program. I think I've found 1 out of 15 visually. Now, we're going to segue in a bit to somebody who's been doing the imaging and has done quite well with that. I've done the Herschel 400. I've done the second Herschel 400, not necessarily according to the Astronomical League's requirements, but according to EVAC's requirements. I have not attempted the Hickson or the Berkeley or the double star program or any of these others. There's another, let's see.
It's at the top of the page.
Okay.
The EVAC winner.
Oh, okay. There's a link here to the generic observing sheet. And this allows you to document very carefully for each object that you observe. This is not a requirement to get an award for EVAC or an observing program. However, it has lots of information that you might find useful in the future if you say, well, let's see, I think I observed this way back when, let's see what it was like. And then it gives you a place to draw what you saw. Amateur astronomers or even professional astronomers way back when, this was their way of documenting what they did, is they made a drawing. So now I want to go back, and that might be interesting.
No, it's going to be easy. Go to right here. So it takes you to the next slide. No, it did not. Which one were you on? That one?
Yes.
There we go.
So here's 3 examples of observing logs. We'll just look at one. The planetary observing log.
Let's go back to that. I can go back to this one. It's this one. Was the one you
Middle one, yeah.
Okay, let's go to there. And then put your mouse there and scroll. Do you want the form itself?
Right.
Okay.
Thank you.
There we go.
So this is the bare minimum of information that you need to know in order to do this observing program. You'll have to look up each of these objects to determine its coordinates, right ascension, declination, which is the way I usually do these. Or if you want to do star hopping, you can get a star atlas or an online program and find your way around that way. So.
You want to go back?
Yeah.
So yeah, just go to here. Just go click here. And you're now back on your presentation.
Okay. Okay. So when you've completed your observing list, send it to me and I'll put your name in for an award. So, any questions? Well, I hope I've given you reasons to try an observing program at least. The next presenter is going to show you what can be done because of all the awards that he has achieved. Thank you.
Things that you can get for accomplishing working with the lists. And I was talking to him about, as Wayne knows, I've done most of the lists that are on the EVAC site as well as on the Astronomical League. And I have this wall. All the picture isn't showing for some reason. Oh, I know why. We've got something there at the bottom. There we go. I was going to say we should see the light switch. Where to go? There it is. But anyway, the Astronomical League, when you complete a project, they send you an 8.5 by 11 certificate. And that's all fine and well. What are you supposed to do with it? Well, some people say throw them up on the wall, and those are your, and you can create an I love me wall. And if you do very many of these projects, you love yourself a lot. You can cover a whole room. Well, my wife said that's not going to work. So we took the certificates and scanned them and reduced them, and we made little certificates. And then we made projections. So I left the light switch in as an illustration of the comparable size of what you're actually looking at, a small portion of the wall. But each one of those certificates on the left is an Astronomical League project. The Astronomical League, which we belong to. And you can work with their programs if you become a member of the Astronomical League, which I think basically runs about, what, $5 a year, or is it 5 or 7? $7.50, such a deal. Anyway, the ones on the right are all the EVAC completed programs. So if you complete an EVAC program, you get a plaque. My first introduction to the plaque was Howard Israel. You heard his name a little while ago. And what those plaques were originally designed for is for taking and putting on and mounting literally to your telescope. And Howard Israel had an 11-inch Celestron, and it was covered with those things. And I looked at it and I said, what in the world are you doing? He says, oh, those are my observing lists that I've completed. That was my first introduction to them. I said, what's this all about? Well, I was mentioning to Wayne, when I first started attending the star parties and things, you would always hear the same questions repeated. We should have got a recorder out and just copied it down and played it back. What's up tonight? What can we go look at? It's an amazing how many people really don't know. They haven't got any list of targets. You might say, well, just take your telescope and point it at the sky. What have you got? Because it's all out there. But what I discovered was they have these observing lists, and usually there's about 100 objects on a list, sometimes less, several times more. But they list all the stuff, and you have it with the RA and the deck. And then you can determine what's up each night, and you have things to go look for. Instead of asking what's up, you ask, okay, is it visible? Go look at it. In my case, I image everything, but other people will do visual. Both worlds exist and both are fine. But that's what you can get back. The EVAC awards are the gold plaque type things. The Astronomical League Awards are 8.5 by 11. And if you look at each one of those 8.5 by 11s, you'll see a pin stuck onto it. Astronomical League is very big on awarding you a pin to go with it. I haven't figured out what to do with all the pins, so we just stuck them on the awards. But anyway, Wayne, there you go. That's what the awards look like for observing programs. Anyone know what that is? Show of hands if you know what that is. Something everyone's been reading about. That's our current headline thing that's out there now, what's in the sky. Okay, and what we're looking at is C 2022 E3. Okay, let's see if we can pronounce this one right. Zwicky? Okay, and that's not really its name. That's the name of the observing facility that actually discovered it. We haven't come out with a formal name for this guy yet, to my knowledge, but everyone keeps referring to it as Zwicky. And that's one of the better pictures or images that's out there that's generated a lot of interest. Where can I look? Where can I see it? How can I image it? What's going on there? And that's kind of what I'm going to be talking about. Okay, slide 1 or 2. Here's where you can see it. I've charted this all out. And if it's red, forget it. Okay. Right now, it's in our southern skies, but it's a fast mover. Now, you can see it if you want to get up at 1 o'clock in the morning, 2 o'clock in the morning, all the way out to 5 a.m. It's still dark at 5 a.m., so it's a good time. And it's out there where you can see it. So it's there. And if you want to consider looking at it now or are willing to get up, I've shown for those who might want to try looking with binoculars, and a lot of people are having success with that. I've shown this as azimuth and elevation. That'll at least get you into the right direction at the prescribed times. Others want to use their telescope, and you have to have a way of entering into your telescope the RA and deck. So I am also showing the RA and deck for each one of the times. So if you're visual, you know where to look. If you want to use your equipment, you know where to look. That, by the way, how do we describe our web page where we have the conversations that are going all the time? Is it the YouTube? No, not YouTube. No. Facebook. On our Facebook page, the EVAC Facebook. This chart is pasted so you can have access to it. I'll give you another way in a few minutes, but it's out there in the list all the times. Things to notice, starting in the end of January. This guy's a fast mover, and he's coming into our skies. And starting about the, what's the date that's actually clear? January. Anyway, starting on the 28th, the Comet will be in I'm trying to think of the term and it's escaped me. It's hell to get old. Where it's always in our sky, circumpolar. We don't have to wait, get up at 2 in the morning to go find it. If the sun's gone down, it'll be there. You can look up and see it. Round the clock if you could in the daytime. Anyway, it's going to be there. And all during the month of February, it's going to be there in our evening hours, which are much more convenient for us, as well as the morning hours. So this chart gives you the reference of where you want to be looking for to find it. I'm going to give you some additional information a little bit later, making it maybe somewhat easier to try and find. But hopefully that will be helpful to you. Okay, I'm going to try and get into where I can select the pictures.
Okay.
And I'll zip through them real quick.
So we're
I
going to
have
stop
images.
sharing.
Few comments. And the question is, what are you going to see? And what can you do? And as he's trying to get that in there, there's really 3 ways to work on imaging a comet.
Dave, get the microphone.
It's just lean over there so you can hear.
3 ways to try and image a comet. If you want to just look at it with binoculars, that's one way, that's easy. But if you're going to do it with a camera, you're going to have to take a long exposure, typically 2 to 3 minutes to work with comets. That means you're going to be guiding. You can guide on the comet, there'll be an effect. I'll show the effect. You can guide on a star, different arrangement, different result. I'll show you the effect. And then I've got a list of comets that I've worked with, and I can show you kind of how I've seen them over the past couple of years. Are we there?
Not exactly.
Yeah.
But I can't get it to show up there. There it is. So it's there. It's on the screen. Yes.
Okay, that's the path of the comet in case you're curious. And the path of the comet is shown by date. There's an interesting one I want you to observe, and that's down there towards the bottom. In addition to showing the date and where it's at, there's a name of something familiar to all of us that's near and dear to us. It's called Mars. Yes, the comet is going to pass right next to Mars. Make note of the date, February the 11th, okay? And that happens to be for an early evening. You'll be able to find it. We're into February, it'll be there, it'll be visible. If you're working with binoculars, Mars isn't too hard to find. You go out in the early evening around 7 o'clock and you look almost straight overhead, okay? It's big and it's red. Right next to it, I'm not kidding, right next to it, if you're working with binoculars, you'll find the comet. That's a good way to get a reference to it, okay? It's going to be close to that before and after, but March the 11th is a good key. On January the 29th, there's another one that's going to make it easy to find. That's not on this particular chart, but you know how we can take the 2 stars in the Big Dipper and we can point to Polaris? And if you follow that line and go along that line on January the 29th, halfway on the transit of that line, halfway, you'll find the comet. You don't have to know too much about the sky and where to look, but if you know, most of us know about the Big Dipper, the 2 stars, and the alignment with Polaris. So there's 2 good references for you. There's only one requirement to make it work. We've got to talk to Mother Nature. We've got to make sure the clouds leave us alone. What I will do, this is on my webpage, and I've got links to the path that you saw, the chart that we saw. There's an interesting sky safari video that just came out today that I've got a link to. It's about a 15-minute video, well worth the watch. It'll talk about where to find it, not how to image it. And then at the bottom is the Comet video links. That's what I can't show you because we're out of time.
I'm going to introduce our main speaker, Dr. James Jackman. James is a postdoctoral scholar at the School of Earth and Space Sciences at ASU. James earned his PhD in astronomy and astrophysics at the University of Warwick in the United Kingdom.
James is a first author on numerous publications and has been an invited speaker at Harvard, MIT, NASA Goddard, European Space Agency in Chile, and many other universities. Amazing for a young fellow. A short story about how I met James. EVAC members here, Bob Buckheim, John Wetmore is on Zoom. And a small group of us here in the US and in Europe have been spectroscopically and photometrically recording and measuring flares on red dwarf flare stars. We wanted to begin to understand what we were seeing. Our friend and team member, David Boyd, put out some feelers around the UK for an expert on red dwarf flares. David Boyd is the former president of the British Astronomy Association, and so he knows a lot of people in the UK. And James Jackman came highly recommended, but there was a problem. James was not actually working in the UK. Actually, he was living in the UK, but he was working for ASU. COVID restrictions prevented him from traveling to the US. So the problem worked out great for our project and I hope for James. Here's Dr. James Jackman. Please give him a warm round of applause.
Thank you very much. And I see someone's been reading my CV. Hello, everyone. As Woody said, my name is James Jackman. I'm a postdoctoral researcher at ASU, working in the School of Earth and Space Exploration. And I'm going to talk to you today about the work I've been doing there on studying stellar flares from low mass stars. But before we get to stellar flares and way before we get to low mass stars, I'm going to first talk about a star that is very close to home. Which way to scroll? Oh. This one, the sun. We all live in the Phoenix metropolitan area. We're all very aware of the sun. And we're all very aware of this view. And another view of the sun is this. So this is the photosphere of the sun, the visible surface of the sun. Broadly featureless, although we can see some darker regions associated with sunspots, regions on the photosphere where heat transport from the interior has been suppressed by the solar magnetic field. Below the photosphere are a number of layers. The sun, like an onion, has layers. In the center is the core, where nuclear fusion occurs. Hydrogen is fused into helium, releasing energy. The photons then travel outwards through the radiative zone. And as they do so, they are absorbed by electrons in the interior plasma and scattered, slowly losing energy in each interaction. And the radiative zone gets cooler as you go outwards. Eventually, that gives way to the convective zone, where convection is the dominant mode of energy transport. In the convective zone, we get these big plasma cells that move up, and as they do, they release the kind of transport their energy upwards into the surrounding plasma, and then they cool and descend back down to the base where they are heated up again and ascend. And we actually see that the top layer of the convective zone is at the photosphere. And this would have been an animation. And on the layer of the photosphere, we can even see this with observations of the sun. We can see that solar granulation of plasma, these cells rising up and then descending back down into the darker intergranular lanes as they cool. And it's very much like a lava lamp. Above the photosphere, there are a couple more layers. There's the chromosphere, which is a thin, less dense layer of the solar atmosphere. And then above that is the solar corona. The solar corona is an incredibly tenuous or very low density plasma that it has a temperature of about 1,000,000 Kelvin. It extends much further out from the sun than the photosphere and the chromosphere. And normally, because of its low density, because of the low density plasma associated with the corona, while it's incredibly hot, because of its low density, it has a low luminosity. Can often only see, as we're aware, can only see the corona during solar eclipses, such as the one shown here, where the moon blocks out the visible disk of the sun. Now, you can see in this image, you can see the plasma associated or light associated with the corona, but you can also see that it follows certain kind of lines and tracks. And that's because the plasma in the corona is an excellent tracer of the solar magnetic field. You can see the kind of lines at the north and the south, which are similar to kind of a bipolar magnet, where the lines come out of the north and travel around to the sun, or around to the south rather, of the sun. And then you can see there are more complex features around the edge. And these complex features are present because the solar magnetic field isn't just a simple dipole. The sun has a complex magnetic field that's generated within its interior. On the top right is an image of that solar corona now in X-rays, and each one of those white lines is modeling of the solar magnetic field. You can see these complex loops that come out of the solar surface and stretch across through the solar corona. The solar magnetic field is generated in the interior of the sun, and it's twisted up by differential rotation. The equator of the sun rotates faster than the pole. And what this does, in the radiative zone, the sun rotates as a solid body, and these magnetic field lines can kind of move out and nothing really happens to them. In the convective zone, this differential rotation occurs, and those field lines get twisted up. And as they get twisted up in the solar interior, they eventually pop out of the photosphere and are rooted in there. And that's what gives rise to this complex geometry we see, and lots of all these magnetic field loops popping out of the solar photosphere out into the corona. And that's what's shown here on the bottom right, this kind of cartoon. And at the roots of these solar magnetic loops in the photosphere, that's where these sunspots occur. The magnetic field is what inhibits the convection, or inhibits the energy transport from the lower layers, from the convection zone, resulting in that cooler, less luminous area. Now, these sunspots, as the sun rotates with the differential rotation, and then also the convective cells moving up, moving plasma out of the way, these sunspots pairs can undergo random walks. These field lines can become twisted. In the photosphere, where they're kind of set in place, where they're frozen in, these lines will never really come together. There's not much risk of that happening. But up in the corona, where these loops really extend outwards, these field lines can become very twisted, and can, in some cases, if you have enough twisting or enough shearing, oppositely directed magnetic field lines can come together. So what happens when that happens? What happens when oppositely directed field lines come together? Well, magnetic fields have energy, so they don't just cancel out. What happens is an event called reconnection. Magnetic reconnection occurs when oppositely directed field lines are pushed together. The field lines don't just cancel out. What happens is they undergo this process called reconnection, and they instantaneously, a way of thinking about it is they instantaneously break apart and then suddenly reform. They reconnect. As they do so, as they reconnect, they will, as with most things in physics, they will shift to a lower energy state. So we know nature, it likes to be lazy, likes to save as much energy. If it was socially acceptable, I'd be giving this talk while lying down. So what happens is the field lines come together, they reconnect, and you can see here the arrows indicating an initial state of field lines being pushed together. That being pushed together might be the movement of the field lines as twisted up a single loop. As they reconnect, they then move back outwards. When the energy is released, this is what causes a flare. So flares occur when reconnection happens and release energy into coronal plasma. This is a diagram on the right-hand side showing a kind of broad schematic of what happens during a flare. I don't expect you to obviously memorize this, but this is an example showing the field lines rooted in the photosphere at the bottom, and then kind of being pushed together up in the corona, creating this X point where reconnection occurs. When the energy is released, electrons and protons in the surrounding area are suddenly accelerated. They travel along the magnetic field lines and they accelerate downwards to the denser chromosphere and photosphere. When these charged particles impact the dense chromosphere, they are suddenly slowed down. And as they slow down, they have to lose their energy and momentum. When this happens, they deposit that energy into the surrounding denser chromosphere. That heats the chromospheric plasma up to a temperature of about 10 million degrees Kelvin. Some of that plasma evaporates, rises up, and fills the newly reconnected field loops. That's this red arc here. And they emit strongly in X-rays. At the same time, that heated photosphere, or the heating of the chromospheric region, results in backheating of the photosphere. Now, the backheating of the photosphere causes regions, again on the photosphere, to be heated to a temperature of about 10,000 degrees, on the order of 10,000 Kelvin. And that emits strongly in ultraviolet and in optical wavelengths. And it's actually this optical emission that was the first observed signature of a solar flare. In 1859, on the 1st of September 1859, Richard Carrington and Richard Hodgson independently observed what they called a singular appearance on the solar surface. Richard Carrington was an astronomer making observations of sunspots on the solar surface. He suddenly noticed that over the space of 5 to 10 minutes, there was an intense brightening. On the right is a picture that I took when I was fortunate enough to actually see his original handmade or hand-drawn diagrams of sunspots at the Royal Astronomical Society Library in London. But then here's a scan of the same diagram for clarity. The ABC and D regions are where he noticed these sudden brightenings. These lasted about 5 to 10 minutes and then they were gone. The next day, there was an intense geomagnetic storm, which we now know was from an associated coronal mass ejection, an outburst of magnetized plasma caused by that flare event. When that coronal mass ejection impacted or reached the Earth and collided with the Earth's magnetic field, the interactions induced electric currents wherever there was a long wire to be found on Earth. In fact, there were reports of telegraph operators being able to disconnect their wires from the mains and run their signals and run their wires and send messages purely off what they called the celestial batteries alone. Now, the Carrington event is typically taken to be the highest energy flare we've ever seen from the sun, or at least from the modern sun. And it's said to have an energy of 10 to the 32 ergs. For those of you that loathe CGS units, that's 10 to the 25 joules, or about 10 to the 12 little boy atomic bombs. So it gives you an idea of the energies that can be released from solar flares. But this Carrington event, we believe, occurs from the sun once every 100 to 150 years. There was an event a couple of years ago that just missed the Earth. So I think we're hopefully all right for a bit. Since then, we've taken a few more observations of solar flares in other wavelengths. And we now know that solar flares emit across a wide range of wavelengths, from radio all the way up into X-rays, and in some cases, gamma rays. But they are very notable in the optical, ultraviolet, and in X-rays. Shown here on the right-hand side is an X-ray observation of that heated plasma or evaporated plasma that I mentioned earlier, that has been evaporated, risen, filled that reconnected flare loop, and emits strongly in X-ray because it has a temperature of about 1,000,000 Kelvin. But since we've taken these observations, not that one. Oh yeah. Since we've taken these observations, we haven't just done it haven't just spatially resolved them. We can integrate them and study them as a function of time. That helps us to understand timescales. And we know that flares occur with a distinctive shape. They have what's called a fast rise and exponential decay shape that will be familiar to some of you in this room. And that flares, like all good astrophysical phenomena, they occur with a power law distribution in energy. On the bottom right is a flare power law distribution, or a flare frequency diagram. The y-axis is the number of flares above a given energy per day, and the x-axis is the flare energy. And like I said, it looks like a straight line because it's plotted on a log-log or logarithmic diagram. And like all good astrophysical phenomena, when we do it like that, we get a nice straight line that's easy to fit. But since then, we also know that flares appear to occur on really any type of star that has a convective envelope. Because since then, we've not just been looking at the sun, we've also pointed telescopes outwards and to observe other types of stars, and we spotted flares on those. And when we see flares on other stars, funnily enough, we don't call them solar flares. We call them stellar flares. Let's drop down a bit. There we go. We call them stellar flares. But the kinds of observations that we get from other stars are somewhat different to those we get from the sun. As we're aware, we can resolve the sun. We can resolve the flare. We can get fantastic observations of individual flaring regions. We know exactly where the flare occurred, and we know exactly what its energy is and its timescales. Observations of other stars. The star sits on a single pixel, so we get the combined sum of all of the quiescent flux plus the flare light. So if we want to try and extract parameters and properties like energies, we need to make assumptions about the model, like flare models of the flare spectrum. And a widely used one in flare literature and in later habitability studies, one that I will come back to repeatedly in this talk, is a black body spectrum. So we assume the flare region is a perfect emitter with a temperature of 9,000 Kelvin. Now, as I've alluded to, we see flares from other stars. And so we need to ask the question, are the flares from other stars? We may be using a model that's kind of based on solar observations, but are all stellar flares like solar flares? And that kind of comes back to the sun is a star, but not all stars are like the sun. There are a variety of different stars out there. And there are stars ranging from O all the way down to M, which is the spectral type depending on the temperature. And the stars that I'm interested in are M stars. M stars are literally and figuratively cool. They comprise the majority of stars. They have masses less than half of the solar mass. And because they are less massive, they don't have to fuse as much hydrogen in their cores to counteract the pressure due to gravity. So they have cooler temperatures and they have smaller radii. Because they have cooler temperatures, they have deeper convection zones than the sun. Or relative to the sun, the convection zones form a greater amount of their stellar interior. The transition between radiative and convection zone occurs at a set temperature. The cooler stars, that gets closer and closer to the core, and eventually below a certain mass, 0.35 solar masses, these stars don't actually have a radiative zone. They're fully convective in their interior. So you have the core, and then you have a convective envelope, and that's the interior. So these stars have great whopping big plasma cells moving up and down, churning up the magnetic field, resulting in incredibly strong magnetic fields, much stronger than we see from the sun. On average, the quiescent stellar magnetic field from some of these M dwarfs can be on the order of kilogauss. And that's the quiescent magnetic field. Whereas for the sun, it might be a Gauss or so. Like these things, their magnetic fields are strong. And because they've got strong magnetic fields, they can regularly have high energy flares. And we've observed these in optical, ultraviolet, X-ray, and beyond. M stars have been found to be able to flare with energies equivalent to the Carrington event or greater on a weekly to monthly basis. On the right-hand side is a optical flare. It's a flare rate of a M star called EVAC, this was taken using the TESS instrument that I'll talk about in a bit. Again, on the y-axis is the number of flares above a given energy per day. The x-axis is your flare energy. And the number 32 there corresponds to the Carrington event. Now, this is assuming that flare model, that 9,000 Kelvin black body model. But it gives us an idea that for this star, a Carrington event occurs once every couple of days, once a week or so. So these stars can flare with incredibly high energies, much greater than anything we've ever seen from the sun. Now, I mentioned M stars are cool. Obviously, this hopefully is just reason enough for why they're cool. But they're also cool to exoplanet astronomers. They're also of interest to exoplanet astronomers because of their cool temperatures. Their low temperatures or their cooler temperatures mean their habitable zones are a lot closer in than for the solar system. Bless you. On the right-hand side is a depiction of the TRAPPIST-1 system. It's a 7 Earth-sized planets around a 0.08 solar mass star. It has a temperature of about 2,000 Kelvin, whereas the sun is about 5,800 Kelvin. But you can see 3 Earth-sized planets reside within the habitable zone, but the entire system sits well within the orbit of Mercury. As a result, astronomers waiting for transits to occur where the planet passes in front of the star to try and characterize the radius of the planet, to see how much light is blocked out by the planet as it passes in front of the star, or characterize molecules in their atmospheres, looking for biomarkers. Astronomers looking for these type of habitable zone planets to assess their capability for life, they don't have to wait as long for a transit. They're much more amenable to the kind of follow-up missions, such as the James Webb Space Telescope, or the extremely large telescopes that are going to come online in the next few years. So the shorter orbits means we don't have to wait as long for a transit to occur. But because these planets are so close in, they're going to be subject to those flares I mentioned. And because they're so close in, those effects are going to be exaggerated. And those effects particularly come into their own for habitability in the ultraviolet. The ultraviolet effects on the habitability of these planets kind of falls into two regimes. There's the near ultraviolet, the ultraviolet light that's closest to the optical. This may have some beneficial effects. The low temperatures of these stars means their spectrum is shifted more towards the near infrared. Certain chemical reactions that are needed to create the precursors to the precursors to the precursors to life, they may require some amount of near ultraviolet light as to kind of kickstart them, to get them going. It's been hypothesized that flares could provide this if the M stars flare often enough. Yet at the same time, the far ultraviolet flux, so the light in the spectrum that's closer to the X-rays, that may simultaneously, so the light from the same flares, they may destroy biomarkers, the biomarkers that the astronomers are actually looking for. So if we want to understand the habitability of these systems, we need to understand the UV flare energies and the UV flare rates of these stars. And also, it's also just quite fun to understand these UV energies and rates just for the sake of understanding them. So to get direct measurements of UV flare energies and UV flare rates, we need to use instruments that reside in space. We need to use the Hubble Space Telescope, HST, or we need to use SWIFT at the moment. If you're not familiar with SWIFT, SWIFT is designed as a rapid response mission for gamma ray bursts. It's equipped with a gamma ray telescope, an X-ray telescope, and a UV/optical telescope, but it has been used for studying stellar flares because it can give us ultraviolet photometry and spectroscopy. But the problem with these are expensive, and accurate characterization of UV energies and flare rates, the ones that we might need for studying the habitability of a wide array of systems or characterizing UV energies of these stars, requires many orbits, making it a very expensive and time-consuming task. So if we want to understand the UV activity of these stars, how else can we go about it? Well, if we go back to that model I showed you earlier, I highlighted here the foot points, the heated regions on the photosphere. I mentioned earlier that during the flare, these regions are heated, and they're heated to temperatures of on the order of 10,000 Kelvin, 5,000 to 10,000 Kelvin. And they result in strong optical and ultraviolet emission. And in fact, currently we believe that the optical and ultraviolet emission is broadly dominated by the emission in this region. So if we can find a model that describes both the optical and the ultraviolet at the same time, some sort of spectral model, a function of the light as a function of wavelength, describes the optical and ultraviolet emission simultaneously, we could calibrate that model in the optical and use it to predict the ultraviolet light, avoiding the need for expensive direct UV observations. And thankfully, optical observations of flares are plentiful. We can get them from wide field exoplanet surveys, such as Kepler, NGTS, TESS, Everyscope, so on and so forth. All of these provide wide field and long baseline continuous observations. When I say long baseline, for instruments such as TESS and Kepler, I'm talking weeks, months, or even years for individual stars. And wide field, these things will observe tens of thousands of stars at any given time. The instrument I've been using most often, or using widely in my work recently, is the TESS mission, the Transiting Exoplanet Survey Satellite. It launched in 2018 and is now on its second extended mission. It observes in quite red optical wavelengths, and it obtains data in month-long sectors, obtaining data in strips on the sky, and it gets full publicly available full-frame images and publicly available short cadence postage stamps. Anyone in this room could go and download the data. It's a US taxpayer-funded mission. You've already paid for the data. You might as well go and take it. In my work, I've been using the short cadence postage stamps, specifically those that have a cadence of 2 minutes or 20 seconds. And this was going to be an animation of how TESS observed on the sky. What it would do is it takes this kind of strip, as you can see here, it has 4 cameras. Each camera observes a different area on this strip. And then at the end of a month, it swivels around and just keeps going, observing more and more of the sky. And in fact, at the end of its first year of operations, this is what it had observed, the southern hemisphere, showing just how much data it had taken. And you can see some of these regions have been observed in one sector, but you can see there's lots of areas there are overlap where stars will get more than one sector of observations. So some data in here will have, some stars in there will have years of data already. So we take this data, we could use it to calibrate the model that describes the optical and ultraviolet emission, and use that to predict the UV light. So again, we take the test light curve. There's an example of a test light curve on the bottom left. If you went and downloaded the data for an active M star, this is similar to what you would see. Each one of these spikes is an individual flare with that distinctive fast rise exponential decay shape I showed you earlier, showing that at least on the face of it, they share similar timescales and similar kind of shape characteristics to white light solar flares. If we calibrate the ratio between an assumed model and the quiescent spectrum of your star, calibrate that ratio in the test band pass, so take the ratio of the model and the spectrum in the test band pass, calibrate it to the amplitude that you measure in your test observations. You can do that for every point within an individual flare, calculate the total, and you can integrate over all wavelengths and all times and get the total energy. Here I've called it the bolometric energy, and it's the same thing. Bolometric total just means integrated over all wavelengths. Here, shown here on the bottom left, is that 9,000 Kelvin black body model that I mentioned. It's based partially off solar observations, but also partially off of observations, spectroscopic observations of flares from active M stars. In red is the wavelength coverage of the test mission, and then in blue and orange are the near ultraviolet and far ultraviolet wavelength regions. Now, if you know the fraction of energy that your model emits in these given UV regions, you can take your lovely power law that you fitted to your flare rate, and you could adjust it. Oh, I've got to stop trying to use the arrow key. You can adjust it and predict a UV flare rate. And just like that, you have a UV flare rate that you could use with a habitability study. You could use it to predict study how an atmosphere might respond to the impact of multiple flares. You could use it to compare how UV flare rates maybe evolve with time by taking stars and measuring how their optical emission evolves with time. And this could just generally provide a way of avoiding the need for expensive direct observations. And in fact, some studies are already doing this in terms of the habitability. They're taking models such as this, combining them with optical observations, here from K2 and Everyscope, where K2 was the follow-up to the extended mission of Kepler, measuring a flare rate, and then comparing it to limits from biological studies to see whether the flares provide that that near ultraviolet light I mentioned earlier to kickstart those chemical reactions. And this star here, this is actually the TRAPPIST-1 system. And this study found that TRAPPIST-1 doesn't flare often enough for life to be driven, or abiogenesis or pre-Bartic chemistry to be driven by flares alone. Either it has to be driven by something else, or we need to go back to the drawing board. So this potentially could be the end of my talk. But you may have twigged that the UV flare rate that you predict, it will depend on the model you choose. And there are a variety of different models available in the literature, each with varying levels of complexity. The model that's most widely used in the literature is the 9,000 Kelvin black body. It's this model here, the one I keep harping on about. It describes the continuum emission at the photosphere, assuming the region emits perfectly like a black body. But we know in the photosphere there's at least hydrogen there. We know hydrogen emits at quantized energy levels. We know we know that it emits with the Balmer series. So we know that flares emit with they have emission lines. You have the Balmer lines. There are emissions in ultraviolet. We know from previous observations that there are emission lines in iron, magnesium, silicon. And in fact, the Balmer lines can even stack up together and form a new continuum in the ultraviolet. And these are factors that models should take into account. And there are other models that try and go one step further and use archival spectra that may have simultaneous observations in the far, near ultraviolet and partially in the optical, and try and stitch them together with this black body to then match it up to the TESS observations that we have. But unfortunately, this archival spectra, we only really have good data for one flare from 1985. So there's only so much we can do with it. So there are a number of different models available on the literature. Each one of them will predict their own UV flare rates. And what makes this even worse is that we know that there are some discrepancies with all of the models. As I just mentioned, we know that flares have emission lines. So the continuum-dominated models that are so widely used in studies, they don't include these lines at all. And we can see here, this, on the right is optical spectroscopy of a flare from an active M star. The blue line is a black body fit to the optical spectrum. And you can see the Balmer series, which are those sharp spikes, resulting in the Balmer continuum. The Balmer series occurs when hydrogen energy levels in hydrogen, electrons drop down to the n=2 level. As you go from up to higher and higher electron shells, and they drop down to n=2, those electron shells get closer and closer together. So the energy, the difference in energy becomes less and less, and eventually they just kind of stack on top of each other at n=infinity, resulting in a new continuum. And also, more recently, we found that flares don't have a single fixed temperature either. Their temperature evolves with time, and that some observations using multicolor photometry in G band and with TESS, or in B band and with TESS, have found that they can have temperatures that go well above 9,000 Kelvin. In some cases up to 20,000 or even 40,000 Kelvin at their peak, resulting in much stronger ultraviolet emission than a single average temperature of 9,000 would suggest. So all of this suddenly calls into question the UV predictions that we're making in these habitability studies, which is bad. But also, it means that we have an opportunity to better understand the flare physics that's going on with these high energy events, which is good, because understanding physics keeps me in a job. So how do we do this? How do we test these models? How do we test the UV predictions? Well, as I said, getting new observations is expensive. So why look for, you won't hear this from a politician, why look forward when we could look back? And instead mine the GALEX archives. GALEX was the Galaxy Evolution Explorer. It was a UV mission that observed over a 9-year period in the near and far ultraviolet. Now, GALEX was, as the name suggests, it was designed for observing galaxies. And it observed when it was in the Earth's shadow. It observed for about up to half an hour per visit. And it observed in kind of sparse time, it observed patches of the sky over this 9-year period. Now, when it observed, it may not have observed the same patch of sky repeatedly. It may have observed one patch of sky, swiveled off to do something else, observed another patch of sky, and then maybe a couple of months later, or even a couple of years later, come back to your original patch of sky. Meaning, it's kind of difficult to use it for measuring UV flare rates for a single star. But early on in the mission, it was shown that you could use GALEX data to measure UV, to detect UV flares from individual stars. In 2006, Welsh et al. Used GALEX to measure flares, observe ultraviolet flares from 4 nearby M stars. To get these observations, they had to get the inclusion of the science team and get GALEX to observe in a specific way, or to rather reduce the data in a specific way, making it difficult to get new kind of observations or new kind of study this, making it difficult to study this on a larger scale. Since then, in 2016, a colleague of mine, Chase Millian, created the G-Photon Python package. It's an open source package that enables anyone to create UV light curves from the archival GALEX data. Like with the test data, you could go home, install GALEX or install G-Photon and go and create UV light curves of your favorite star. As I mentioned, GALEX observed quite sparsely across the sky, so it's difficult to measure UV flare rates for an individual star. But because it observes so much of the sky, you can use it to measure kind of average or to study UV activity in a statistical way, study average UV activity for a large sample of stars. Because you might, instead of having 10 flares from one star, you might have 1 flare from 10 stars. And that was shown in 2019. A study used GALEX with the G-Photon Python package to study the near ultraviolet properties of flares from stars that had previously been observed in the Kepler field of view. Shown here is the ultraviolet amplitude versus duration of these flares, showing that for some stars, the flare could outshine the quiescent star in the ultraviolet by a factor of 1,000, showing that these things, on one hand, these things were very bright, and on the other hand, in the ultraviolet, these M stars are quite dim. But when this happened, we realized that we could use archival data to test the models in the way we wanted. Oh, and they measured an average flare rate, which is fantastic, because we could use GALEX to study the ultraviolet activity of these low mass stars. And to get the optical data, we could use TESS. We could take GALEX observations of M stars and now take contemporary TESS optical observations of the same M stars, measure the average optical flare rate with TESS, combine it with models from the literature, use them to predict the UV flare activity of those stars, the average UV flare rate of those stars, and then compare the predictions to what we actually observed from GALEX. We did that again, showing this kind of pictorially, measure the average optical flare rate with TESS, here for the 9,000 Kelvin black body model, use it to predict the near ultraviolet flare rate and the far ultraviolet flare rate as well for GALEX, and then compare that to what we observed in the GALEX light curves, to what we actually measured in the average UV light curves from GALEX. And then we could use those to calculate correction factors for models that would tell us about the physics at work. And that's what we did. We did this for a variety of models, but the results I'll show you are for this black body model I've been talking about. On the right-hand side, the black line is observed UV flare rates for low mass M stars. On the top are 0.4 to 0.5 solar mass stars. These are ones that have some amount of a radiative envelope in them. They're partially convective. And then 0.1 to 0.3 are these fully convective stars, the ones that have incredibly strong magnetic fields. The red lines are the predicted UV flare rates from combining the TESS with literature models, literature flare models. And we find that the partially convective M stars, those slightly higher mass, low mass stars, they require a correction factor of 2.7. That means we have to multiply the predicted energies by 2.7 to bring them in line with observations. And then the lowest mass stars, a factor of 6.5, suggesting that for some reason our models, that the lowest mass stars, their flares actually emit more UV light than their higher mass counterparts. In the far ultraviolet, we only got data for the lowest mass stars, for those fully convective ones. But we found that in the far ultraviolet, where the most damaging effects are held, that 9,000 Kelvin model underestimated the energy by a factor of 30, suggesting that it really wasn't doing a good job. So what does this mean? Where do we go from there? Well, flare models underestimate the ultraviolet light by up to an order of magnitude. Not great news for habitability studies, at least in the far ultraviolet. And we believe it's kind of due to two reasons I've mentioned already. One, emission lines contribute quite strongly in the UV. I mentioned that the Balmer jump results in that Balmer continuum. That continuum stretches into the UV. It will contribute to the energy budget. So that needs to be taken into account by models. We can't ignore it any longer. And then also, maybe that could explain the result for the partially convective stars, but it couldn't fully explain the result for the fully ones. So maybe higher energy flares from low mass stars have higher temperatures as well than previously assumed. Maybe the temperature is a function of mass. So they underestimate the UV energies, and we need new models. And how else? So we need new models, but how can we get the information to inform those new models? We need to disentangle the degeneracy between the emission lines and the temperatures. And to get that, we need new observations. And thankfully, to measure flare temperatures, we can do that just using optical observations. We could target stars that we know are being observed with TESS, and we could take another telescope and observe them in another filter, similar to that Howard sample did earlier. But we could do this, if we did this for really long periods of time, we could build up such a large sample of flares, really characterize flare temperatures, see how they evolved as a function of time, and maybe see whether average flare temperatures are above 9,000 Kelvin, just on average. Maybe we just got that wrong. Maybe we didn't base models on enough observations. Unfortunately, larger observatories will often not observe stars for more than a few nights. making it difficult to build up the large samples of flares that we need to build these new models. Well, if large observatories won't observe them, sod them. We'll go to small observatories. And maybe we can target bright stars that can be observed from smaller telescopes on the ground. Maybe we'll get people in this room to observe stars that are bright enough to be observed from the ground, and take color measurements of flares that are previously being observed with TESS, that we know are being observed with TESS, to measure what we can call pseudo-continuum temperatures. If we have stars that are bright enough in the B band to be observed from the Phoenix area, we could do that using a pro-amateur collaboration. And that's exactly what we're doing. Members in this room are part of the Red Dwarf Group, a global collaboration of amateur astronomers studying flare emission. Many members in this room, and even on this Zoom call, can take observations using telescopes that they own, take B-band photometry or even spectroscopy as well, to study flare emission. If the star is also being observed with TESS or being observed by another amateur in a different filter, the two-band photometry can be used to measure flare temperatures. If you can sit on a star for long periods of time, days, weeks, months if possible, can really build up the samples of flares that we need for building new models. To do that, again, to measure these pseudo-continuum temperatures, we'll take the ratio between the fluxes in two filters. Here on the right, I've shown examples for the TESS in red and the B band in blue. On the right is a 4,000 Kelvin black body and a 9,000 Kelvin on the bottom, showing an exaggerated example of how the cooler black body emits more in the red, the hotter one emits more in the blue. But if you can take these measurements, you can measure temperatures. And that's what the group has been doing. The group has been taking observations over several months, and my gratitude cannot be measured because this data has been given to me on a plate. It's absolutely fantastic. But the group has been taking this data, and so far for this work, I've analyzed 44 flares from M stars that have been observed by the Red Dwarf Group with both B-band and TESS photometry. I've been doing this, I've been able to measure flare temperatures between 8,000 and 14,000 Kelvin. On the right-hand side is an example of observations by a member of our group, where the TESS light curve is on the top, and then the simultaneous B-band light curve is on the bottom. And we can compare it to the TESS and Everyscope sample I mentioned earlier from the Howard et al. This Everyscope is a private collaboration, a survey that's observing almost the entire southern sky almost every other night. They get G-band photometry, and they published a paper in 2020 that detected 31 flares from M stars. Combine the sample, our analysis, we've already built up a larger sample, and we're measuring similar temperatures. And we can use this to measure an average flare temperature and see whether, like I said earlier, did we get that average temperature wrong? Is the average flare temperature above 9,000 Kelvin? Aha. We're still measuring an average temperature of about 9,000 Kelvin. So maybe the average is fine. Maybe there's something else that we need to take into account in the models. It doesn't solve our problem, but it points to solutions. And it says that if we're going to persist with a single temperature model, as I said earlier, we need to include emission lines. We need to include the emission lines. And I didn't mention it in this talk, I didn't cover it in this talk, but spectroscopy that's being taken by members of the Red Dwarf Group is helping with this by getting us a better understanding of how much flux is emitted in the Balmer series. And if we're going to improve our models any further beyond that, models should probably include some sort of temperature evolution, including higher temperatures at the peaks of flares. Because we didn't just measure the average temperatures of the flares measured by the Red Dwarf Group, also measured maximum temperatures. And we've measured maximum temperature between 9,000 and 30,000 Kelvin in our sample. That 30,000 Kelvin, to give the same amount of flux in the TESS bandpass, it results in 20 times more near ultraviolet flux at the peak of the flare than we predict just from a 9,000 Kelvin model. But that's just at the peak of the flare. The question is, does that last long enough? And does that last long enough? And does that occur regularly enough across all types of flares to, when we combine it with emission lines, does it occur often enough? Does it last long enough to match that discrepancies, match the UV energy discrepancies that we measured earlier? So where do we go from here? Well, we still need direct UV observations. As much as the archival UV observations are great, they only give us a statistical sense of what flare energies are. If we want to catch corner and edge cases, direct observations are still needed. Hopefully HST and SWIFT in the immediate future, and hopefully for far in the future. But beyond that, potentially CubeSats as well. I'll give a shout out to a CubeSat mission that's being led by my boss, Evgenia Shikolnik at ASU. She's the PI of the SPARKS mission. It's a 6U CubeSat that will obtain near and far ultraviolet photometry of a group of low mass M stars, and it will observe each one for at least one stellar rotation. If this can be combined with optical photometry from the ground, then that could give us some fantastic panchromatic data for stellar flares, helping us to solve some of these questions that I've been bringing up in this talk and improve models which can then be fed back into our overall understanding of stellar and solar flares and our understanding of the habitability of planets around other stars. And with that, I will conclude. Thank you.
We have questions. Sure we might. Tom?
Anyone has a question, you'll need to use the microphones or Zoom people can hear the question.
Oh, I'll ask, when does Sparks launch?
So Sparks is still going through some of the, so this is something that you will, unfortunately, while I work at ASU, I'm not a member of the Sparks team. Sparks is going through still some of the kind of mission design state, or not mission, it's designed, so some of the kind of mission approval stages. But I think it's due to launch in, I want to say in, I mean, what year is it now? It's 23 now. Probably like, the number that's jumping out at me is 2025, but the all the information is available on the ASU website. So it is all available for you to look. And also, I mean, I can give you Evgenia's email and you can just email her and ask, hey, when's it going to launch? Because we know what NASA is like. These things, there's a chance it could get pushed back.
Other questions?
Yes, sir.
What kind of equipment do the amateurs who are helping you out need in order to be able to provide something that's useful to them?
You could ask the man behind you.
I think he's referring to me. I'm doing photometry with a 4-inch refractor with B filters and B filters. That's why I asked earlier what size telescopes you have. Obviously, an 8-inch, a 10-inch, a 20-inch would shorten the amount of time that you have to spend on a target. The key on this from our amateur pro-am point of view is many hours of observations following a target through the night. The bigger the aperture you have, the shorter the exposure. The shorter the exposure, the more detail we can tease out of these flare events. As James described, they rise very rapidly and then they decay exponentially, but slower than that rapid rise. And if we can get shorter exposures, we get a better picture of the shape of that flare. That's from the photometry side. I do spectroscopy with a 20-inch telescope on these targets, but there's excellent work being done with people with telescopes as small as probably 8 inches in terms of spectroscopy.
So something I will add on the note of the flare rise, if I go back to, let's say, this plot here. So this flare rise, I mean, maybe this wasn't the greatest example because this flare rise is pretty well resolved, but you can see that the decay lasts a lot longer. But the flare rise is when the energy is being deposited down in the photosphere and the plasma is really being heated up. And it's really this region where those hottest temperatures are often recorded. In the decay, that's when the plasma is then cooling back down, which may be why we're still measuring this lower 9,000 Kelvin as an average, because it's just that measurement's dominated by the decay. So if you're able to use your instruments to resolve the rise, that could really provide the information that studies need for building those new models. Because if we find that oh, every single flare, it reaches 40,000 Kelvin during the rise. We've just never been able to get the data for it. Then we can put a new model in and say, okay, temperature is a step function at 40,000 Kelvin. And then as soon as you hit the decay, drop down to 9,000 and go down. So, but it really is anything you can offer is the benefit is just getting the extra wavelength coverage and the numbers of flares.
So Rick, you can
Okay.
try talking.
So what is the B-band wavelength to start with?
B-band wavelength.
B-band wavelengths, if I'm not mistaken, is about 3,800 to about 4,800 angstroms, I think. Yeah, I'm getting a few nods in the room.
Okay.
It covers, so the B-band does cover some of the Balmer series. If I go to this plot here, it covers maybe from the drop, it might actually be broad, no. Yeah, it covers on this plot, probably about 3,800 to about 4,800 and does cover some of these emission lines. So this is why I use the term pseudo continuum in the talk, because we're still fitting black bodies to the total flux we measure. So the temperatures we measure may still be slightly overestimated because they have some contribution from emission lines. Although some of the work I've been doing, again, with the Red Dwarf group where we have simultaneous B-band photometry and spectroscopy, we've been able to isolate the flux from the emission lines. And I've estimated that it probably comes, at least for the flares we're observing, comes to an order of at most 10% of the flux. So it's not as big probably not too much to worry about, but yeah.
Okay. The reason I ask is Tom Oz and I are working on a system where we're using narrowband filters and single photon detectors, and maybe we can make some modifications to do some of these measurements.
Can you talk louder, Rick?
I don't think so. I think it's about as loud as I can get.
Okay. We're having trouble hearing your follow-on question.
What I'll do as well is I'll stop messing around with the slides. If I leave my email up there, obviously anyone, if you have any questions as well, do feel free to email me. I mean, you could tweet me as well, but then everyone will see your question. So
I do have one question for you.
yes,
So the Red Dwarf group, when you write a paper, do they get to be co-authors?
of course they do.
Awesome.
Yeah, anyone that's provided data or even helped out with the analysis or is part of the Red Dwarf group, I believe will be free to be on any papers. If you've put the time in, then you deserve to be on the paper. I mean, at least that's the way I look at it. There might be people, I don't know, maybe looking at Bob, he's laughing.
So we've got another online question from Thomas Smith, who's actually in our Red Dwarf group. How can others join in the Red Dwarf Flare project? Talk to Bob Buckheim here.
Yes, that's right. Send me an email.
Bob's a EVAC member. And these targets that we've been working on, EVAC, ADVO, CR draw, a couple of slides that James has shown up here, they tend to be magnitude 10, magnitude 11 targets. So if you've got equipment that and a camera and a good mount and a V or preferably B or even a U filter, then you can likely take data that would contribute to this project. And the key, as I've mentioned before, is many hours of observation following that target. We sort of have this guessing game of who's going to get the whopper flare, and you observe and you observe and you don't get one, and half hour after you quit, somebody in a different time zone is on it and they get the whopper. How the cookie crumbles. Any other questions?
Or you get such a big flare that it appears to break tests, is what we've once found.
Thank you, James.
You're very welcome.
Yeah, thank you, James. That was really interesting research and an interesting project that some of the members are involved in. Our next meeting on February the 17th is a little different at the start. We have a swap meet. The swap meet will start at 7 p.m. If you want to participate in the swap meet, it would help if you could send me an email just to make sure we have a table and a spout set up for you in the room. From 7 to 7:45 is the swap meet. This is for individual members. It's not club equipment. You make a deal with whoever is selling the equipment. And we will have more information on that in the Observer. So check that out, and we have some other information if you've signed up for EVAC Announce. I do have to personally say, though, when you mentioned the Red Dwarf group, I keep thinking of the cast of Red Dwarf, the BBC comedy series from years ago. Do any of them have a silver H on their forehead, or evolved from a cat? I don't know. Anyway, anything else? Any other questions or whatnot? Thank you. Glad you came tonight. It's good to see you. Check with me on any of the observing the outreach programs, or contact Wayne about any of the observing programs, and we'll be posting some material from Dave on the Comet and some of his other pictures. Thank you. Have a lovely evening.